Hello, my name is Jacek and I'll be presenting the work we did at Amazon Search this year, and it was driven by our intern Azin and our collaborators from AWS and University of Hanover. Ranking and retrieval systems play a critical role in information discovery. These systems aim to maximize the relevance of the retrieved object for their typical users, which unfortunately can introduce bias against minority groups. To evaluate fairness of ranking with respect to demographic groups, such as ethnicities or gender, we must first find the group memberships of all items in the ranked lists. In other words, we need to learn the sensitive attributes, known as labels, such as ethnicity, gender, associated with each element. Unfortunately, collecting such membership labels may be costly, operationally challenging, or even illegal in some cases. So let's consider an example of a job candidate search. In order to understand whether a bias towards one ethnicity exists in the list of candidates, we need to know the ethnicity of all of them. However, some kind of candidates might not be comfortable with providing such information, and soliciting such data may be illegal in some cases. In these situations, sensitive labels may be inferred using a machine learning model, and such labels will be known as proxy labels, or are known as proxy labels. And unfortunately, evaluating fairness using proxy labels can lead to unreliable assessments due to prediction errors. So, in this example, the first person has been incorrectly classified as African American, leading to potentially an erroneous evaluation of bias. So, let's consider the ranking we have presented here. Using a simple metric such as fractional representation in top 4 based on the real group assignments, we can see that the ranking is biased against African Americans. However, if those results, so our representation in top 4 metric, was evaluated using the incorrect predicted proxy labels, we could decide that everything is in order and the ranking is balanced. So in this work, we would like to address the problem of group fairness assessment of ranking based on proxy labels. So knowing that the proxy labels might be noisy and not always correct. Going forward, we will outline the assumptions necessary to estimate the true bias from one computer based on proxy labels, and show how the real bias can be recovered from proxy measurements. Let's discuss our problem setup. We are concerned with measuring fairness of a ranking process. We start with a distribution Q over two variables S and A, where S represents the ranking scores used to sort items in the list, and A is the binary sensitive attribute that partitions the population into two groups. And Q is a joint distribution over S and A that we assume exists. Using a process, a ranking of size n is generated by sampling n independent elements from Q, getting S and A for each one, and then sorting them according to the ranking scores S. Now, our goal is to reliably measure fairness of this process using some metric m in situations where we only get to observe the proxy label A hat instead of A for items in the generated ranking. So, the two notions that I will frequently use in this talk are the true measurement, which is the value of metric m on our ranking process, having access to the true binary valid sensitive attribute, and the proxy measurement, which is the value of our metrics, but computed only observing the proxy labels A hat. And the main question that we would like to answer is, would it be possible to recover the true bias measurement only knowing the proxy bias measurement? Before going into more details, I would like to introduce the metrics we use to measure group fairness. These metrics were they pairwise or listwise. For pairwise metrics, such as pairwise demographic parity, a ranking is fair if the sensitive attributes of two randomly chosen items do not reveal any information about their relative ordering. Listwise metrics, such as exposure and R&D, take into account the fact that users' attention to different positions in the ranking follows a skewed distribution. So it's not equally likely that the user will inspect an item at the top or at the bottom of the list. So for the second class of metrics, with an example being exposure, the ranking is fair if an item observed by the user has the same probability of being assigned to any of the groups. And for the third class, an example being the R&D metric, the ranking is fair if the distribution of group memberships at the top of the list matches the global one. So, going back to our main problem, we would like to know if we can recover the value of fairness metrics computed based on the true values, having only access to proxy measurements. So first we investigate the data model, which is the relationship between the three variables S, A hat, and A. So we show that without making any assumptions about the other underlying data model, it is impossible to decide whether ranking is perfectly fair or maximally unfair, and hence just observing S and A hat. And hence the proxy fairness measure can be arbitrarily different from the actual value. So for those interested, the actual proof can be found in the paper. It's unfortunately a little bit too lengthy for this presentation. So, equipped with this proof, we identify two assumptions under which we can compute the relationships between the true and proxy measurements. The first assumption imposes a conditional independence between A hat, so the proxy labels, and S, so the scores, given true labels A. So we expect this assumption to hold if the proxy model is trained on features that are conditionally independent of the score, given the true values. One example is when we predict a person's gender from their name and compute their ranking score based on some cognitive tests that are unrelated to the name. In the second one, the conditional independence is between true values A, true labels A, scores S, and proxy labels A hat. And we expect the assumptions to hold if the dependence between A and S is mediated through the proxy labels A hat. One practical example is when machine learning models for predicting S are trained on engineered features derived from the sensitive attributes to break the causal link on the outcome of the model. Causal effect on the outcome of the model. Working under the assumptions we have defined, we can show that there is a linear relationship between the true and proxy measurements. In other words, it is possible to recover the true measurement having access only to the proxy one. So for assumption 1, we can derive the exact relationship using the group conditional error rates, which are P and Q, as well as the fraction of groups of individuals with the binary sensitive attribute equals to 1, which is beta. So the algebra unfortunately becomes a little bit convoluted here. So I invite the audience to take a look at the paper for the detailed derivation of this formula. But what is important here is that as long as we can access the conditional accuracies, conditional error rates of the proxy model and some rudimentary statistics of the set of all items, we can recover the real values of bias measurements having access only to the proxy measurements. And so it's important to know that an equivalent formula can be derived for data model under assumption 2, and it is presented in our paper. So we evaluate our new findings on selected real-world datasets to show its correctness, while additional evaluation on synthetic datasets can be found in the manuscript. So we evaluated assumption 1 on two external datasets, Goodreads authors and the FIFA players dataset, and the assumption 2 on the Compass dataset and IBM HR analytics dataset. So to evaluate our bias correction method, we first split the dataset into 3 partitions. The first one, having 60% of the data, is the trained dataset for our proxy models, and is also used to compute the population demographics. So next, the second 20% is used to compute the error rates of the proxy model and generates the P and Qs, so the conditional error rates or conditional accuracies if you prefer. And finally, we generate our actual ranking using the last partitions. And for the last partition, we compute the proxy labels for individuals using the proxy model trained on the first partition, and estimate the proxy bias using predicted proxy labels, and finally find out the correct value using the previously provided formulas. So, as for metrics of success that we would like to use, we compute the errors of the proxy and the corrected measurements. So we want to find how far away the proxy bias is from the actual bias and how far away the corrected proxy bias is from the actual bias. And what is more, we provide the ratio of these two values. So this ratio is higher than 1 if the error of the corrected bias is higher, and lower than 1 if the error of the proxy bias is higher. So we evaluate assumption 1 on two datasets, as we've said before, the Goodreads authors and FIFA dataset. So for the Goodreads authors, we use the gender of authors as a sensitive value and predict the proxy labels from names of the authors. And for FIFA dataset, we use the nationality as the sensitive value, make it binary, so we only evaluate German versus English, and predict the proxy labels from names of the players. So for both datasets, we expect the conditional dependence between the proxy labels and scores given true labels, because a person's name is generally conditionally independent from features that determine the number of fans and their value in euro as a footballer. So the results show that for all the metrics, the error of the corrected measurements, they're shown in blue boxes, are closer to 0 compared to the errors of the base proxy values shown in pink. In other words, we observe that the corrected measurements are much more accurate than the naive proxy values. Similarly, the ratio of errors is consistently below 1, meaning the corrected values are indeed closer to the true values than the base proxy ones. So we evaluate assumption 2 on two other datasets, Compass and IBM HR Analytics. To enforce the second assumption, we predicted ranking scores using the learning to rank model that we trained on proxy labels along with features independent from the true labels. So this way we could mediate the dependence between the sensitive attribute and the ranking scores through the proxy labels and thus satisfy the second assumption. So these figures again show that the corrected bias yields much more accurate estimates for different proxy models and different metrics. Again, the corrected values shown in blue are closer to 0 than the base proxy measurements shown in pink. So finally, we compare our method against a recent approach for estimating bias based on crowdsourcing. So the baseline crowdsources the ground truth attribute values for a small sample of items in the ranking and uses them to predict the bias for the whole list, instead of relying on proxy labels. So in the plots, we have the corrected bias, which is ours, shown in blue, and the weighted sampling baseline shown in pink. As you can see, for both assumptions, the baseline becomes comparable to our bias correction methods only at the higher sampling rates of above 40%, meaning almost 1 in 2 items need to be actually evaluated to find the ground truth in order to get comparable measurements. So we can conclude that our method is much more useful in situations where crowdsourcing is expensive, it's not free, but proxy level can be easily gathered by, for example, having an ML model trained to predict the labels. Even if the model is not 100% accurate, our correction method still allows us to get very good estimate of the real errors. So, to conclude, in this work we studied the feasibility of bias estimation in ranking when proxy labels are used. We identified 2 feasible assumptions of the data model, and for each we've derived the relationship between the proxy and the true measurements, having access only to the conditional error rates of the proxy model and rudimentary statistics of the population. And finally, we use these relationships to correct the bias values and evaluate the bias correction method on real-life data sets. And we show that the method in fact works in practice. So anytime when proxy labels are available with known error rates, this method can be used to find the true values of bias. So finally, we invite the audience to read through our paper in full, as there are some interesting details we had to skip over to meet the 15 minutes timeline for this talk. Thank you very much.